We're now ready to look at section 3.7. In the textbook, this section is called Operation on Functions. So let me just go ahead and start looking at a problem I'm going to work, and we can talk about it. So we've already learned about function notation. So now we're going to start looking at problems that involve two functions. So for this first problem, f of x is going to equal 3x minus 2. But now we have a second function, g of x, which is going to be x cubed. And what this problem wants us to do is to do 4 mathematical functions with these two functions. You notice how the word function is used a lot. It can be sort of confusing. So the first thing we're going to eventually do is, here's how the notation is. F plus g, which means we're going to add the two functions together, but we want to add them together with the value of x being 3. So this is the way it's written. And the next thing we're going to be asked to do is to take the function f and subtract the function g, and also evaluate that when x equals 3. And then the third problem, which now you can probably guess, fg, this means f times g. We're going to multiply the two functions and once again evaluate them when x is 3. And we'll finish up, obviously, if we're adding, subtracting, and multiplying. Then the last one is going to be f over g, or this also means f divided by g, and once again evaluated when the function is 3. Now, when you approach each of these problems, there are 2 ways to go about it. And for this first problem, I will show you both ways. And then for the rest of them, I would do it what I think is the easier or more efficient way. So let me go ahead and show you what I mean. This first problem, where we want to determine what we get when we add the two functions together and evaluate them at 3. You can also think of this as you can take the f function and plug in 3 for x, and then you can add it to the g function and plug in 3. You'll see in a minute, normally to sort of do it this way is usually simpler, but I'm going to show you both ways. And by that, what I mean is, for now, let me just go ahead and let me add these two functions together in their current form. So really, probably, just to be more precise, let me write it like this. I'm going to add f of x and g of x. So f of x is 3x minus 2, and g of x is x cubed. So if I add them together, this is what I get. And of course, sometimes in math, most of the time we like to write things in descending powers. Just sort of looks nice that way. So this would be f of x plus g of x. Of course, you notice that I haven't evaluated anything for x. So now if I'm going to do this problem, this could be my first step. And then if I want to take f plus g evaluated when x is 3, of course, I've already added f and g together, which is this. So I could just plug in 3. So x cubed becomes 3 cubed. plus 3x. I'm plugging in 3 for x, so it's 3 times 3, then minus 2. So once again, this function here is my f plus g, and now I'm evaluating that when x is 3. So 3 cubed is 27 plus 9 minus 2. What is this? 36, 34. If I don't mess up on the math. Now, so this is one way to do it. This, in my opinion, can be a little more work than an alternate way. Because what I did here was I added the functions together, leaving the variable x in here. I had to do some algebra. Now, this wasn't too bad, but in future problems, to do it this way can get sort of messy. The other way to do it is, instead of adding the functions together with the variable x still here, I can do this. I can take the f function and plug in 3, and take the g function and plug in 3, and then simply add those together. The idea here is I'm trying to get rid of my variable x as soon as possible. So basically, I want to determine this. This should be the same as this. So f of 3, I simply take my f function, which is way up here, 3x minus 2. I plug in 3 for x. 3 times 3 minus 2. 9 minus 2 is 7. And then I want to do g of 3. Here's my g function, x cubed, plug in 3 for x. 3 cubed, which is 27. And now I simply have to add these together. 7 plus 27 is 34. So hopefully you can see it's usually almost always easier to immediately plug in your number for x, and then you go ahead and do the operation. So for instance, for the second question up here, f minus g evaluated 3, and I'm going to go ahead and just take f of 3 minus g of 3. Now I've already determined what these are, right? F of 3 I said is 7, and g of 3 is 27. So f minus 3 of g is negative 20. And I can just keep doing that. So the third one is the f function times the g function evaluated 3. Now just to prove the point, if I went ahead and tried to multiply these out before I plugged in the numbers, I would have to do this multiplication here. I mean, it's not horribly difficult, but still, why not just go ahead and say f of 3 times g of 3. F of 3 we know is 7. G of 3 is 27. If I take a chance and do this in my head, 140, I think it's like 189. In other words, this is still easier than having to deal with all this stuff here. So the last one, f divided by g evaluated when x is 3. So the f function is once again 7. The g function is 27. I don't think this reduces, so that's it. So initially, taking two functions, adding, subtracting, multiplying, dividing, not too difficult. And if you're asked to evaluate it at a certain value of X, the sooner you plug in the X, the easier it gets. Now, a big part of this section is this thing called composite functions. So here's a new, let me just, in a minute, I'm going to work this problem. So f of x is going to be 2x squared, and g of x is going to be x minus 3. And the first question they asked me, they want to determine f. Here's something new, this little empty circle. This does not mean multiplication. This empty circle means a composite. Sometimes we say F composite G. Now, I'm going to write out in a minute what a composite function consists of. And every time I have to do some kind of a composite function, I always rewrite this, because to me, when I rewrite this composite function, it makes it not very difficult. Here's what a composite function means. F composite G means I take my F function, and what I'm going to do is inside my F function, I'm going to replace X with the G function. So F composite G really means take the F function, and every place you have an X in the F function, you replace it with the G function. So let's go ahead and do that. So here's my F function, 2x squared. So 2, now I'm going to do x squared, but instead of x, I'm going to replace x with the G function. You know, we learned function notation. If I had done f of 3, then I would replace the x with the number 3. Well, instead of putting a number in here, I'm going to replace the x with a function. So here's my f function, 2 times x squared. The x becomes the G function. Right, so 2x squared becomes 2 times the G function squared. So that's what a composite function is. Now, maybe when you do this kind of problem in the homework, they may want you to multiply it out. So x minus 3 squared is x minus 3 times x minus 3. And I believe, if I don't mess up, this is what you get. And if you multiply the 2 out, your final answer should be something like this. So now they give a second question. So here's what they do now. They say G composite F, once again, with the X here. So once again, I always rewrite this because to me, it just makes it a pretty straightforward problem if I rewrite it G of F of X. So this means I'm going to start with the G function, which is right here. And whenever I have an X, I'm going to replace it with the F function. So the G function is x minus 3, but instead of x, I need to plug in the F function. Right? So here's sort of my x, and then the G function is x minus 3. So this was the original G function. and I replace the x with the f function. And in this case, then this is your final answer. And then just for fun, they'll do things like this. They'll say, how about f composite f of x? So once again, I always rewrite it. What I'm going to do is I'm going to take the f function and then replace x with the f function again. The f function is 2x squared. So 2 and x squared, but I'm going to replace x with the f function, which is 2x squared. Right? Hopefully this makes sense to you. Now, if I want to simplify this, the 2 gets squared, the x squared gets squared. So 2 squared is 4 times 2 is 8. And I believe it should be 8x to the 4th. And then just to finish things off, they give you one last g composite g of x. So once again, that's g of x. So my g function is x minus 3. So instead of x, I'm going to replace it with the g function. So it's x minus 3 minus 3, right? Because this is like my x minus 3. This is the original g function, but I replaced the x with the g function again. So when you're all done, you should have x minus 6. Now here's something that's interesting. Let's do a composite function problem, but now we're going to replace x with a number. So we're going to evaluate it. So here is a problem. F of x equals 3x squared plus 4. G of x equals 5x. Let's do f composite g at x equals minus 2. Now, just like when we did this very first problem with operations, you can always treat it like an algebra problem and leave your variable in and do all the algebra. And then the last step, plug in the number. Or you could, let me write it out so it's clear what I'm saying. So basically we're doing f composite g of x, which if I rewrite this means f of g of x. Now you could take the f function here, 3x squared plus 4, and replace the x with the g function and do all the algebra, and you would end up with this composite with the value of x, and then plug in -2 for x. You could do that. However, what's much simpler is, for this problem, just go ahead and say f of g of -2. So in other words, what I'm going to do is I'm going to go determine what g of -2 is. I'm going to take the g function and plug in -2 for x. That's actually pretty simple, right? 5 times -2. So g of -2 is going to be -10. So now this becomes f of -10. And once again, just to skip a few steps, now take my f function. If I plug in -10 for x, -10 squared is 100 times 3 is 300. should be 304. So look how much simpler it is to go ahead and plug in the numbers as soon as possible, as opposed, I didn't even do it here, but you can imagine. I mean, basically, I'll write it out. I'm not going to do it. It would have 3x squared. You'd have 5x squared plus 4. I mean, it's not a horrible problem, but it's not as simple as just this. So I'm saying when I do these kinds of problems, as soon as possible, I will plug in the number for x, and it just makes it a lot simpler. Let's do one more. How about G composite F of 3? So once again, I'm going to rewrite this composite function as a G of F of 3. So what I'll do, let's go figure out what F of 3 is. So if this is the F function, F of 3, if I plug in 3 for x, 3 squared is 9, 9 times 3 is 27. I believe F of 3 is 31. So if F of 3 is 31, then this becomes G of 31. So now I go to my G function, plug in 31 for x. So 5 times 31, if I don't mess up in my head, I believe should be 155. All right, composite functions are not too bad. The whole key is, and I do this myself, whenever I see a composite function, I always rewrite it like this, because this to me, I understand and can work it out. So F composite G of -2, I always rewrite F of G of -2. All right, so that's composite functions, not too difficult. Here's a problem. You'll have a problem like this in your homework. Let's just do it real quick. One more sort of composite function problem. What they do here, they give you a function for f of x, which is x squared minus 2. And they give you a function g of x, which is x plus 3. And here's what they do. They now want you to solve. They do a composite, f composite g of x equals 0. So now this is an equation, and we're going to solve it. And our goal is to figure out what value of x makes this true. So now I'm going to have to do f composite g, leaving the x in there. And then once I get this equation, I'll have to solve it. So f composite g of x, once again, I rewrite it as f of g of x. So my f function is x squared minus 2, but in place of the x, I want to replace it with the whole g function. So the x squared becomes x plus 3 squared. So x squared minus 2. So this is now this composite function. Let's go ahead and multiply it out. So this is going to be x squared plus 6x plus 9, and I still have the minus 2. So when it's all said and done, x squared plus 6x plus 7. So this right here is f composite g of x. So I'm going to take this, set equal to 0, and I'm going to solve for x. So x squared plus 6x plus 7 equals 0. I believe this factors. Does it factor? Actually, it does not factor. This is sort of a pain. I'm actually not going to finish this problem because what you would just do is probably use the quadratic equation where A would be 1, B would be 6, and C would be 7. And you could plug them in, but we've done this before, so I'm not going to take the time to do it now. I just wanted to show you how you go about solving this problem. Now, there's one more problem in the homework, and for this one, I'm actually going to, I printed out the homework, and I need to show it to you because it's pretty different, and it's not very hard, but if you don't see what's going on, it can be pretty confusing. I'm going to try and cover up these answers. So this is where they give you two tables. See what we have here. This first table, the top row are values of x. So x can be 5 or 6 or 7 or 8 or 9. And you notice the bottom row is f of x. And what this is saying is you choose a value of x. If you choose x to be 5, that means f of 5 is 8. So whatever value of x you choose, the second row determines what the function is going to be. If I say, well, what is f of x when x is 8? I go to x equals 8, and I go down here and I say, when x is 8, the function equals 5. If I say, what's the function when x is 6? Well, when x is 6, f of x is 7. So here's a table for the function f. Here's a table for the function g. In other words, for the g function, if I say, what is the g function when x is 9? I go to x is 9, and the g function is 4. Now, here's what's interesting. Here's a problem they give you, f composite g of 5, and they want us to use these two tables. Well, let's do this. Let's write out what does f composite g of 5 mean. I'm going to rewrite it. I always rewrite the composite function. F composite g of 5 means f of g of 5. So what you do is, let's go determine what g of 5 is. So what you do is you go to your g table and you say, what's the g function when x is 5? Well, if x is 5 here, the g function is 7. So g of 5 is 7. So I plug 7 in here. And then this says, what is f of 7? I go to my f table and I say, when x is 7, f of 7 is 6. So this whole thing equals 6. Not too hard, right? Let's just do one more. How about just for fun? Let's do g composite g of 5. So if I rewrite my composite function, this means g of 5. So let's go inside first. What is g of 5? I go to my g table and I say, what's the g function when x is 5? Well, x is 5 is here. The g function is 7. So this becomes g of 7. Now I say, what is g of 7? Once again, I go to my g table and I say, when x is 7, the g function is 6. So the answer should be 6. All right, this problem, not very hard once you understand sort of what they're getting at. Now, the last thing in this homework, there are a couple of sort of story problems. These story problems, the principle is like a composite function, but you don't really work it out like a composite function problem. That makes it a little confusing. Let me just show you what the problem is. I want to cover up the answer. You can read that. a fire has started in a dry open field and is spreading in the form of a circle. If the radius of the circle increases at the rate of 4 feet per minute, express the total area A as a function of time. Assume the fire begins spreading. So really what we're doing is, you notice here, what they want to determine is A of T, where A is the area of the field that's been burned, and T is the amount of time. Now, the area of this field is going to be like a circle. So if we look at, if you remember back from geometry, the area of a circle is pi r squared, where r is like the radius, and of course pi is just a number. Now the thing is, this fire is continually spreading, so this circle is continually getting larger and larger. So the area of this circle is constantly changing. It's just not the same. It's constantly getting bigger. And that's why they want to know the area. But inside this equation, there's going to be the variable t, because the size of the burnt circle will determine how much time has passed. So we need to have an equation for the area that involves time, because this area is always changing. So if someone says, what's the area? I will ask them, well, at what time do you want to know? You give me the time that it's passed, and I can tell you the size of the burnt circle. So if this is area, how do we involve the time element? Well, the key is, look at this sentence here. If the radius of this circle increases at the rate of 4 feet per minute. Here's what they're basically saying. The radius 4 feet per minute, and what you do, you multiply it by t, where t is in minutes. When it says it's increasing at the rate of 4 feet per minute, what it's saying to you is basically, if I make it even simpler, the radius is going to be 4t, 4 times the time that has passed, where the time is in minutes. So in other words, if t is 1 minute, at that point, the radius is going to be 4 feet. If t is 10 minutes, 10 times 4, the radius of the circle is 40 feet. In other words, the more time passes, the larger the radius. So what I'm going to do now is, I'm going to now take this little expression and I'm going to plug that in for r up here. So A equals pi r squared. I'm going to plug in 4t for r. Now, if I get rid of these parentheses, the 2 gets applied to both in here. I end up with 16 pi t squared. So therefore, now I'm saying the area of this burnt circle is 16 pi t squared. So you can see how you have to choose a time. So if someone was to say, well, what's the area after 1 minute? Then you plug in 1 for t. And you would say the area is 16 pi. So this is that kind of problem. Then there's a second kind of problem they give you, which is even a little trickier. So this will help you out on the homework, I think. They say the volume of a canonical pile of sand is increasing at a rate of 243 pi cubic feet per minute, and the height of the pile always equals the radius of the base. express the radius as a function of time, assuming that r. So this is pretty tricky because I even had to do it. I had to go look up. So what you've got basically here is so you got this sand dropping down and it's forming sort of like a cone, but it's constantly changing because the sand keeps falling. Matter of fact, they say the volume of this cone is 243 cubic feet cubed per minute. So I can write that as 243 pi times t. That's what that sentence is saying. Saying, hey, if you want to know the volume of this cone here, you plug in the time and I can tell you the volume because the volume is always changing. It's going to be dependent on how much time has passed. So that's what this sentence is saying. But what they want to know is down here at the bottom of this cone, you've got this thing called the radius. And actually, this is the height. Now, there's a geometry formula that we can use that tells us how we can calculate the volume of a cone. And I wrote it down because I didn't know it. I had to look it up. It's volume of a cone is pi r squared h over 3. So to determine the volume of a cone, you have to know the radius of the bottom of the cone, and you have to know the height of the cone. Of course, look what the problem says. The height of the pile always equals the radius of the base. So h is the same as r. So I can replace h with r. So instead of writing h here, I'll replace it with r. And now I have a new equation, pi over 3 r cubed. So the volume of this cone of sand is pi over 3 r cubed. Now up here, I said the volume with respect to time is this, but the volume from geometry is this. What I'm going to do is I can now take this and set it equal to this, since these are both expressions for the volume. So 243 pi times t equals pi over 3 r cubed. Now, my ultimate goal in this problem, I didn't write it. They want us to know, they want us to figure out how did the radius change in respect to time, right? So as this sand is dropping, the pile is growing. Obviously, the bottom of the cone is growing, so the radius is changing. That's what they want to know. So this little equation here, I can solve for r. And when I get r by itself, I will have this answer here. So first of all, if you notice I got a pi here and a pi here, they cancel out. If I multiply both sides by 3, then I'm going to get 3 times 243. I'm going to get my calculator for that. It's going to be like 700 and something. If my calculator worked. Oh, I think my calculator may have died. Perfect timing. Well, you know what you can do? Old-fashioned long multiplication. 9, 12, 729. Now, if I want to solve for r, since I have r cubed, this is a lot of algebra. I have to take the cube root of both sides. So when you do that, you find up with R equals the cube root of 729 is actually my answer, which is 9. So 9 cube root of t, or another way to write it is 9t to the 1/3. Of course, I could write it. All right, that's a pretty tricky problem. So that's a little break for you on the homework if you have this problem. All right, so that was section 3.7 from the book. Hopefully not be difficult for most of you.